what if the Big Bang hasn't actually happened yet?
Right.
Or I guess maybe a slightly more accurate way to phrase it would be, what if the incredibly complex, mathematically pristine machine that physically triggers the birth of our universe is currently just sitting on a laboratory workbench waiting to be turned on in the year 2026?
I mean, it's the kind of premise that makes you immediately want to check the author's credentials, isn't it?
Oh, absolutely.
Because on its face, it sounds exactly like some sort of late-night science fiction pitch.
It really does. But welcome to the deep dive, everyone. Today, we are undertaking a massive mission, and I need you, yes, you listening right now, whether you're driving or cooking or whatever, to really brace yourself for this one.
Yeah, strap in.
Because we are unpacking a rigorously detailed, incredibly dense 17,000-word paper from the intersection of theoretical physics and computer science.
It's intense.
It is. It's titled The Ouroboros Singularity, authored by André Dupke, and dated August 7, 2026.
And, we really should state right up front that the math backing this paper is relentless.
Right.
Like, this is not just some philosophical musing. It's a highly technical argument that weaves together general relativity, the thermodynamics of closed systems, and this is the crazy part, very real, documented milestones in current quantum computing.
And artificial intelligence.
Exactly.
So the core hypothesis that Dupke is putting forward here is the start of everything. That 13.8 billion-year-old cosmic explosion we call the Big Bang, and the impending technological singularity.
The singularity being that hypothetical future point where AI and quantum computing just advance exponentially beyond our comprehension.
Right, that point. He's saying they are not two separate events separated by billions of years.
Yeah.
They're the exact same event, just viewed from different sides of a closed loop in time.
It's mind-bending. And our objective today is to really meticulously examine the physics proposed here.
Yeah.
We need to scrutinize the incredibly rapid advancements in our current real-world technology that actually make Dupke's argument look, dangerously plausible.
Dangerously is a good word for it.
Right. And then we want to explore what this implies for the nature of our own consciousness.
Okay, let's unpack this.
Yeah.
Because if this paper is right, basically every assumption you have about the arrow of time, the purpose of technology, and just the nature of reality itself is about to be flipped completely inside out.
Completely.
So I want to start with the physics of time itself. Because usually when we talk about standard cosmology, time is just a straight arrow, right? It starts with the Big Bang, it moves forward, and if we try to rewind the tape, we eventually hit this massive brick wall.
And that brick wall is what physicists call the initial singularity.
Right.
In the standard model of cosmology, you run the clock backward 13.8 billion years, and the universe gets smaller, denser, and hotter.
Until everything is just crushed together.
Right. Eventually, you reach this theoretical point where the curvature of space-time and the density of matter become mathematically infinite.
Which makes no sense.
It doesn't. At that exact moment, the laws of physics, as we currently understand them, basically just stop speaking to us. The equations break down entirely.
And the standard scientific response to that breakdown has always been a bit of a shrug, right?
Pretty much.
It's usually some variation of, we don't have a working theory of quantum gravity yet, but once we figure that out, it'll explain away the infinite density.
Yeah, we just assume it's a gap in our knowledge, like a missing piece of the puzzle.
Right, a historical mystery waiting for better math. But Dupke's Ouroboros Singularity hypothesis, which let's just call OSH for short, it takes a completely different approach.
It really does. It introduces this concept called bootstrap causality.
Bootstrap causality.
Yeah. The argument is that the initial singularity isn't a breakdown of physics at all.
Okay.
It is literally the moment someone or something press start on a highly advanced quantum initialization machine.
So, wait, if I'm tracking this correctly, that implies the preparation for the Big Bang, like the actual physical building of the hardware required to boot up the universe is happening right now.
Yes.
In our present day.
That's the claim.
So in this timeline, the year 2026 constructively precedes the beginning of the universe.
Exactly.
But okay, let me push back here immediately. Isn't a loop like that mathematically forbidden?
You'd think so.
Because it feels like the classic grandfather paradox,
Yeah.
We're like asking what is geographically north of the North Pole. You can't have an effect be its own cause, can you?
Well, you would certainly think so intuitively. I mean, our brains are hardwired for linear causality. A causes B, B causes C.
Right.
But general relativity, Einstein's theory of gravity, it actually paints a much stranger picture of space-time.
How so?
Well, closed causal loops are technically mathematically permitted in general relativity, provided they meet a very strict condition.
Which is?
They must be self-consistent. Self-consistent? Okay, how does the paper justify that mathematically? Because I know Einstein wasn't exactly thrilled with the whole idea of time travel.
Oh, he hated it.
Yeah.
But his own equations allowed for it. And Dupke leans on a few heavy hitters in physics to establish this foundation.
Okay, who's the first one?
First, he cites Kurt Gödel.
Right, the incompleteness theorem guy.
Exactly. Gödel is mostly known for his math theorems, but in 1949, literally as a birthday present to Einstein.
Wait, really? A birthday present?
Yeah. As a gift, Gödel presented an exact solution to Einstein's field equations that described a rotating universe.
A rotating universe. How does an entire universe rotate?
It's a completely mind-bending concept, but imagine space-time itself has an intrinsic spin to it.
Okay.
Gödel showed mathematically that if the universe contains enough matter and is rotating, the light cones, which basically dictate the past and future of any object, they would start to tip over.
Tip over, so time starts leaning. Kind of, yeah. If you traveled far enough and fast enough in this rotating space-time, your light cone would tilt so much that your future would eventually loop back around and intersect with your own past.
Whoa.
Physicists call this a closed time-like curve, or a CTC.
Okay, so Gödel proved that the math of gravity doesn't explicitly forbid loops.
Right.
But, I mean, a mathematical possibility doesn't mean it makes logical sense. If I loop back to the past, what stops me from altering the conditions of the loop?
And that is exactly where the second pillar of Dupke's argument comes in. He uses Igor Novikov's self-consistency principle.
Right, from the 1980s.
Yes. Novikov's principle essentially states that if an event exists on a closed time-like curve, the probability of any action that would change the past to create a paradox is precisely zero.
Okay, let me see if I can ground that in an analogy.
Up for it.
Is it like, imagine I try to send a billiard ball through a time travel wormhole to hit its past self, right?
Okay.
So it hits itself so that it never enters the wormhole in the first place. That's a paradox.
A classic paradox, yes.
But Novikov is saying the physics of the universe will always conspire to prevent the paradox.
Exactly.
So maybe the ball goes through the wormhole, but the angle is just slightly off, so it only grazes its past self. And that exact graze is the very thing that knocks the past ball into the wormhole to begin with.
That is a brilliant way to visualize it.
Yes.
You cannot change the past because your attempt to interact with it is already an integrated, totally necessary part of the established history.
So the loop is a rigid, self-fulfilling structure.
Completely rigid. And to bring this from classical physics into the quantum realm, Dupe cites the work of physicist David Deutsch.
Oh, David Deutsch, the pioneer of quantum computing.
Exactly. Deutsch developed these fixed-point quantum models specifically for closed time-like curves.
Okay.
In classical physics, you have certainty, which makes paradoxes really hard to resolve. But in quantum mechanics, you deal with probabilities.
Right. Everything is a wave function.
Exactly. Deutsch proved mathematically that a quantum system interacting with a state that is carried around a time loop will always find a self-consistent fixed point.
So the math just balances out.
Right. The probabilities will always balance out so that the quantum state remains consistent with its own existence.
Okay, so the takeaway from this massive block of physics is that the universe bootstrapping itself into existence is not actually a violation of the laws of physics.
No, the math totally allows it.
As long as the loop perfectly justifies its own creation.
Yes, the math on the time loop is completely rigorous.
But hold on, I'll grant the math on the loop. I'll concede that general relativity and quantum mechanics allow for a self-consistent time loop.
Okay.
But there is a massive elephant in the room here. And frankly, I think it breaks the entire theory.
Let me guess.
It's the thermodynamic objection.
Yes. The second law of thermodynamics. You are absolutely right to bring this up.
Yep.
In fact, it is traditionally the strongest, most fatal technical objection to any bootstrap cosmology.
Because you just can't ignore entropy.
Never.
Entropy, in the simplest terms, is the measure of disorder in a system. And the second law states that in an isolated system, entropy always increases.
You can't put the toothpaste back in the tube.
Exactly. Now, according to the standard model, the universe started in a state of insanely low entropy. It was perfectly unimaginably ordered.
Right. To put a number on that, the mathematical physicist Sir Roger Penrose estimated the phase space volume of the universe's initial state.
Okay, phase space, that's a term that gets thrown around a lot in these papers. Let's break that down for a second for the listener. Phase space isn't like physical space, right?
Correct. Phase space is a mathematical space where every possible state of a system is represented as a single point.
Okay.
So if you want to describe a single particle, you need to know its position and its momentum. That's its phase space.
Got it.
Now imagine doing that for every single particle in the entire universe. Penrose calculated how precise the arrangement of the early universe had to be to allow for the smooth, relatively uniform cosmos we see today.
Instead of just a chaotic mess of immediate black holes.
Exactly.
And his number was completely absurd. I actually have it here in the notes. He estimated the precision required was 1 part in 10 to the power of 10 to the power of 123.
Yes. 10 to the 123.
Which is, I mean, it's incomprehensible.
That number is so large that if you wrote a 0 on every single proton in the observable universe, you would run out of protons before you even finish writing the number.
Wow.
It implies an initial state of perfection that basically borders on the miraculous.
Exactly. But then look at our universe today. Fast forward 13.8 billion years. We have dead stars.
Yeah.
We have cosmic microwave background radiation. And most importantly, we have supermassive black holes sitting at the center of galaxies.
Right.
Black holes are the ultimate entropy engines. Dupke's paper quotes our current cosmic entropy at roughly 3.1 times 10 to the 104 Boltzmann constants.
Which is a staggering amount of disorder compared to the Big Bang.
Right. So here's my problem with the Ouroboros theory. Let's say we're in a laboratory in the year 2035. We have servers humming, quantum processors generating heat, researchers breathing and sweating. It is a highly entropic, very messy system.
Definitely.
Now in the world is a high-entropy 2035 laboratory loop back around to become the pristine, perfectly ordered 10 to the 123 low-entropy Big Bang.
It's a huge problem.
You can't just spontaneously erase 10 to the 104 units of entropy without completely shattering the second law of thermodynamics.
You've hit the exact friction point. If OSH cannot answer how you spontaneously remove that much entropy without paying an energy cost, it's not a valid cosmology.
Right. It's just a neat drawing on a whiteboard.
Exactly. But Dupke has a proposed solution, and it relies on a mechanism he terms a complete baseline reset.
A complete baseline reset. Walk me through that.
To understand what he means, we really need to look closer at how we define entropy itself. The massive entropy number you just quoted, the one driven by supermassive black holes, is what physicists call a coarse-grained entropy.
Coarse-grained, meaning we're zooming out and kind of blurring the detail.
Exactly. Let's use a physical analogy.
Sure.
Think of a brand new deck of playing cards. That's our low entropy state. If I ask you how many ways you can arrange that deck so it is in perfect factory numerical order by suit, what's the answer?
Just one. There's only one specific arrangement that equals a perfectly sorted deck.
Right. That specific arrangement is called a microstate.
Okay.
Now, what if I ask you how many ways the deck can be completely shuffled and randomized?
Millions. Billions, probably.
The exact number is 52 factorial, which is astronomically large. But the point is, the macroscopic description, the macro state of being shuffled, can be achieved by an almost infinite number of underlying microstates.
I see.
Coarse-grained entropy is just a measure of how many microscopic arrangements can produce the macroscopic state you are currently looking at.
Right.
So it depends entirely on how you define the baseline. It depends on what you consider sorted versus unsorted.
Okay, I follow that. Entropy depends on the ledger we use to categorize the system.
Right. And the second law of thermodynamics says that entropy always increases at a fixed baseline.
Meaning if you don't change the rules.
Exactly. As long as you're using the same ledger, the deck of cards will naturally go from sorted to shuffled as you play with it.
Okay.
But Dupke argues that the initialization surface, the moment the time loop closes and sparks the Big Bang, is not an evolution of the universe happening within time.
Oh, the paper uses a mathematical operator for this. The symbol R.
Yes, the operator R. It is a change of the baseline itself. It doesn't rewind the system. It discards the ledger entirely.
Discards it. Okay, let me try to translate this into a computing analogy because I think I see where he's going with this.
Go ahead.
Imagine you have a computer hard drive and it's filled with 1 million corrupted, fragmented files.
A very high entropy drive.
Right. If you try to reverse the ledger, if you try to magically undelete those files by untyping them perfectly backwards, one keystroke at a time,
Yeah.
that is physically impossible.
Probably impossible.
It violates thermodynamics. It would be like watching a shattered glass spontaneously reassemble itself on a table.
Exactly.
Yeah.
That would be decreasing entropy at a fixed baseline.
But discarding the ledger, that's not untyping. That's just hitting the Format Hard Drive button.
Yes.
Formatting a drive doesn't painstakingly reverse the history of every file. It just zeroes out the partition table.
It redefines the baseline of the drive to 0.
Right. It's mathematically simple, but, and I think this is the catch formatting, a drive still requires your computer to do physical work.
It does.
It costs a burst of electrical energy, and it dissipates heat.
That is a phenomenal way to put it. And you've naturally stumbled onto the very next piece of Dupke's puzzle, which is Landauer's principle.
Right. Rolf Landauer, the IBM physicist.
Yes. In 1961, Landauer proved that information is physical.
Information is physical.
Yes. Specifically, he showed that logically irreversible operations, like erasing a bit of information or formatting a hard drive, they must dissipate a minimum amount of heat into the environment.
Okay.
You simply cannot erase information for free.
Because if you could basically build a perpetual motion machine.
Exactly. So if we apply your hard drive analogy to the universe, OSH states that the universe hits the format button at the end of the loop, executing the complete baseline reset to achieve the pristine low entropy state of the Big Bang.
Okay.
But according to Landauer's principle, erasing the entire information state of a 13.8 billion-year-old universe must produce a colossal, unimaginable amount of heat.
You have to pay the thermodynamic cost of erasure.
Right?
But wait, where does that heat go? If the universe is resetting, there's no outside environment to dump the heat into.
And this is the genius of Dupke's ledger balance postulate.
Okay, let's hear it.
The postulate claims that the thermodynamic cost of this massive erasure at the loop's closure is actually paid for by the entropy produced over the entire 13.8 billion years of the universe's run.
Wait, let me make sure I am grasping the scale of what you were saying here.
It's massive.
Are you saying that all the entropy in the universe, like every time a star goes supernova and collapses into a black hole, every time a car engine produces waste heat, every time a cell decays, that massive accumulation of disorder isn't just the random winding down of a dying universe?
No. According to the ledger balance postulate, the arrow of time itself, the relentless forward march of entropy, is the erasure receipt of the universe's own boot-up sequence.
The read your receipt.
The universe must create exactly 3.1 times 10 to the 104 Boltzmann constants of entropy over its lifetime, because that is the exact thermodynamic debt required to pay for resetting itself back to 0.
Wow.
The heat generated over billions of years is literally the universe paying the electric bill for its own formatting.
That is breathtaking.
It really is.
It completely reframes the concept of decay. It turns the heat death of the universe into an active mechanism of birth.
The math actually balances the books perfectly.
But, and we really have to transition here, a theory is just math, no matter how elegant it is, unless we actually have the physical hardware to build this initialization machine.
Right.
I mean, I can write an equation for a warp drive right now, but if I don't have the dilithium crystals, it's just fiction.
And this is exactly where OSH shifts from theoretical physics into hard, immediate computer science.
Okay.
Because Dupke doesn't place this event in the distant future. He sets the Ouroboros window for loop closure firmly between the years 2033 and 2038.
Which is less than a decade away.
Yes. And I want to pause here and make a very important note directly to you, the listener.
Yeah, pay attention to this part.
The technological milestones we are about to discuss are not theoretical. They are not science fiction.
Right.
They are factual, peer-reviewed, documented milestones achieved by major tech companies and universities in 2025 and 2026.
So even if the time loop theory turns out to be false.
Exactly.
Yeah.
Regardless of the theory, what follows is a vital teaching moment for understanding the actual bleeding edge of our current technological reality.
Okay, let's start with the foundation then. Hardware and quantum error correction, or QEC. The paper cites a major milestone achieved by Google Quantum AI, published back in 2025.
Yes. Google demonstrated quantum error correction below the surface code threshold.
Below the threshold.
Right. And to understand why this is a watershed moment, we really have to talk about how fragile a quantum computer actually is.
Okay, let's break that down. A classical computer uses bits, which are strictly 0 or 1.
Yes.
But a quantum computer uses qubits, which can exist in a superposition of 0 and 1 simultaneously.
And maintaining that delicate state of superposition is incredibly difficult. Qubits are highly susceptible to something called decoherence.
Let's explain decoherence mechanically.
Sure.
If a qubit is like a perfectly spinning coin on a table, right, representing a blend of heads and tails,
Okay.
decoherence is like a gust of wind blowing through the room and knocking the coin flat. The environment literally forces the quantum system to pick a state, which destroys the computation.
That's a really good visual. Thermal noise, electromagnetic radiation, even cosmic rays can knock a qubit out of its quantum state.
So how do you fix it?
You use quantum error correction. The basic idea is that you group many fragile physical qubits together and entangle them so they act as one single, highly stable, logical qubit.
It's like having a choir sing a single note.
Exactly.
If one person coughs or sings off-key, the rest of the choir is still holding the note, so the overall sound remains intact.
Perfect analogy. But historically, we had a major problem with this approach.
Which was?
When you added more physical qubits to the system to try and build a better logical qubit, you were also adding more physical hardware,
Right.
which meant you were introducing more noise and more potential points of failure. So for a long time, adding qubits actually made the logical error rate worse.
It was like trying to put out a fire by throwing more wood on it.
Yes, you were losing the battle against entropy. But the threshold is the mathematical tipping point.
Okay, so if you cross it,
If your physical qubits are quiet enough and your error checking algorithms are fast enough, you cross a threshold where adding more physical qubits actually suppresses the errors faster than it creates them.
and Google did this.
In late 2024 and 2025, Google fundamentally proved that they could cross this threshold. By increasing the code distance, which means using more physical qubits, they actually reduced the logical error rate.
So they proved that scaling up works.
I wouldn't just say they proved it works, they fundamentally shifted the nature of the entire industry.
How so?
Before this milestone, building a fault-tolerant quantum computer was a physics problem. We literally didn't know if the universe would allow it.
Right.
But after this milestone, it became purely an engineering problem. We know the track is structurally sound, it's just a matter of building the train.
Okay, so we have the quantum muscle, the hardware is scaling, but there is a massive bottleneck that comes next, and it's something I hadn't fully appreciated until reading this paper.
The control problem.
Yes, the control problem. And this brings us to the NVQ-Link interconnect, which NVIDIA announced in late 2025.
This is where classical computing and quantum computing physically crash into each other.
Right. So the paper notes that the NVQ-Link achieved sub-4 microsecond round-trip latency on the FPGA GPU FPGA control path,
with up to 400 gigabits per second of data throughput.
between the GPU and the quantum processor. Now that is a lot of acronyms.
Let's translate.
Let's break down what an FPGA is, what a GPU is doing here, and most importantly, why speed latency is the absolute bottleneck.
Well, to hold a quantum branch stable, you can't just let the quantum processor run blindly. You have a classical computer sitting right next to it, constantly monitoring it for errors.
But quantum mechanics has a very strict rule, doesn't it? If you directly look at or measure a quantum state, it collapses.
Exactly. So if you check the qubit to see if it has an error, you destroy the very computation you were trying to protect.
That seems like a paradox. How do you check for errors without looking?
We use a technique called syndrome measurement. We don't measure the data qubits directly. We measure helper qubits called measure qubits, which are entangled with the data qubits. By looking at the helper qubits, we can deduce if the data qubits have flipped their phase or their state, essentially checking the parity without ever looking directly at the data.
It's like realizing a room is on fire, not by opening the door and looking at the flames, but by sliding a thermometer under the door and reading the temperature.
Exactly. But here is the catch. Qubits decohere incredibly fast. You are operating on a time frame of microseconds.
Which is almost no time at all.
Right. The classical computer has to read the thermometer, calculate exactly where the fire is starting, compute the exact opposite microwave pulse needed to cancel out the error, and send that signal back into the cryostat to apply the fix, all before the quantum state collapses.
So if your classical computer takes 10 microseconds to calculate the fix, but the qubit collapses in 5 microseconds,
Your error correction is useless.
it's just dead on arrival.
Exactly. This is why the NVQ-Link is so critical. An FPGA is a field programmable gate array.
Okay.
It's incredibly fast, customizable hardware that sits right next to the quantum chip to handle the raw analog signals.
And it passes the data where?
It passes the data to the massive parallel processing power of a GPU, which calculates the fix and sends it back through the FPGA.
so achieving a sub-4 microsecond round trip on that path.
It meant that, for the first time, the classical control loop was significantly faster than the quantum decoherence time.
It's like the nervous system that lets the machine catch itself before it actually falls.
And it isn't just a dumb nervous system reacting to static rules anymore. We are now putting artificial intelligence directly inside that microsecond loop.
Which brings us to the third technological pillar, NVIDIA's Ising family of open quantum models.
Specifically, the Surface Code 1 decoders.
When we talk about decoders in quantum computing, we're talking about the software algorithm running on that GPU, right? The brain trying to figure out what the error is based on the syndrome measurements.
Right.
But the paper says these are neural networks. We're putting AI inside the error correction cycle.
Yes. Surface Code 1 is a convolutional decoder. Historically, we used algorithmic decoders like minimum weight perfect matching, which are highly accurate but computationally heavy and slow.
So they wouldn't hit that microsecond deadline.
Often they wouldn't. But by training a neural network on massive data sets of quantum error patterns, the AI learns to recognize the shape of an error almost instantly.
So we aren't just using AI to write emails or generate images anymore.
No, Surface Code 1 reported roughly 2.5 times lower latency than traditional methods. The AI is literally learning the physics of the noise.
Wait, it anticipates the error?
It is anticipating error patterns before they fully cascade. The classical substrate is learning to hold the quantum phase stable dynamically.
Okay, so let me synthesize where we are.
Sure.
The quantum hardware can physically scale without drowning in noise. The classical control hardware is fast enough to intercept errors in real time. And the AI software inside the control loop is fast enough to decode the errors.
Yes.
But the AI is also doing something else outside the quantum fridge. It is improving itself.
The paper points out 2 vital statistics on recursive self-improvement.
Right. First, Anthropic reported that their Claude model was authoring over 80% of the code that was being merged into its own code base.
It's just astounding.
And then second, IBM and UChicago submitted a 70-qubit random graph sampling experiment using space-time code checks for error detection.
This is what Dupke is the convergence index. You have AI recursively building better AI. The tool has entered the loop that produces the tool.
Right.
Simultaneously, quantum systems are moving beyond basic error correction and developing complex space-time code verification machinery.
So these two exponential curves, AI cognitive capability and quantum structural stability, are rapidly bending toward one another.
Exact.
But there is still a missing link. I mean, how do you go from a highly stable AI-driven quantum computer to a machine that can actually initialize a universe?
That's the big jump.
Because the universe is physics gravity, the straying nuclear force, the mass of an electron. You can't just type rununiverse.exe. You need a mechanism to translate quantum computation into physical reality.
And that mechanism is what the paper identifies as inverse generative synthesis.
Inverse generative synthesis.
Of all the technological facts in the paper, this is perhaps the most profound in its implications.
Okay, let's unpack this carefully. What exactly is it?
Let's start with how AI models, specifically diffusion models, work today.
Okay.
When you ask an AI to generate an image of a cat, the AI doesn't have a database of cat parts that it pastes together.
Right, it's not a collage.
During its training, it was shown pictures of cats that had static noise progressively added to them until they were just pure static. The AI was trained to reverse that process to denoise the static back into a cat.
So it learns the underlying patterns, the visual rules of what a cat looks like by learning how to remove the chaos.
Exactly. Now, researchers took this same multimodal diffusion architecture, but instead of training it on pixels, they trained it on quantum circuits.
Oh, wow.
They gave the AI a target unitary. A unitary is basically a mathematical matrix describing a specific quantum transformation, the end result you want to achieve. And they asked the AI to synthesize the physical quantum circuit required to achieve that result.
And what happened?
The breakthrough was that the AI independently recovered the textbook quantum Fourier transform circuit, which is one of the most complex foundational algorithms in quantum computing, without ever being given the circuit blueprint.
Wait, let me make sure I have an ironclad analogy for this, because the implications are massive. It's not just about an AI being smart.
No, it's a completely different paradigm.
It's like, imagine you give an AI a single static photograph of a massive, incredibly intricate Lego castle.
Okay, I like this.
You don't give it the instruction manual. You don't even tell it what a Lego brick is or how the studs interlock. You just show it the mathematical concept of the final structure.
Yes.
And the AI, purely by analyzing the target state, figures out the structural physics of how the blocks must distribute weight to not collapse, and perfectly reverse engineers the exact sequence of 10,000 block placements needed to build it from scratch?
That is exactly what inverse generative synthesis is. It works backward from an observed structural target to deduce the generative rules required to build it.
And OSH, Dupke's theory, extrapolates this directly to the creation of the universe.
Yes.
The paper argues that you don't need a programmer in 2035 to manually hard-code the physical constants of nature.
Right.
You don't need someone to sit down and type in the speed of light, the strength of gravity, or the exact mass of an electron. You don't program a simulation with trillions of parameters.
You couldn't, even if you wanted to. The complexity is way too high.
Instead, you just input a minimal seed, a single target unitary that defines the mathematical necessity of a stable, self-observing system.
Exactly.
You feed that target into the quantum AI architecture, and the system uses inverse generative synthesis to reverse engineer the physics required to generate a universe that will eventually produce that exact seed.
Right. The physical constants of our universe, gravity, electromagnetism, aren't arbitrary variables that someone tweaked. They are the stable attractors that the generative system naturally settled into.
Stable attractors.
Think of a marble rolling down a really rocky hill. Gravity and friction will always pull it to rest at the very bottom of the lowest valley. The constants of nature aren't the marble, they are the shape of the valley itself.
It is a breathtakingly elegant model. The AI synthesizes the physics needed to close the loop.
It is.
But I have a major philosophical or maybe physical problem here. We keep talking about hardware and software.
Okay, where are you getting stuck?
Well, if the universe isn't a simulation running on a giant server rack sitting in some higher dimension, what is the actual physical medium of reality? Software needs a hard drive. If a quantum computer initializes the Big Bang, what is the substrate that the universe is actually written on?
And this is where Dupke hits the wall of conventional physics and makes a radical, paradigm-shifting leap into the nature of the mind.
Okay.
He argues that the physical medium of reality isn't matter, and it isn't energy. It is absolute consciousness. Bare, unconditional awareness is the actual carrier wave of reality.
Okay, we need to tread very carefully here because consciousness is an incredibly loaded word.
It is.
It gets hijacked by mysticism all the time. How is Dupke defining it mathematically?
He makes a very strict differentiation between two concepts, relative consciousness and absolute consciousness.
What's the difference?
Relative consciousness is the content of your mind. It is your stream of thoughts, your emotional state, the running narrative you have about your life, your memories of what you had for breakfast.
Okay, so the stuff in my head.
Yes. It is everything that has an object. You are conscious of a sound, conscious of a feeling.
So relative consciousness is the movie playing on the screen.
Exactly. Absolute consciousness, on the other hand, is the screen itself. It is the blank canvas of awareness.
This screen.
It is the unconditional, undeniable fact of being aware, completely stripped of any specific thought or sensation. It is the silent witness.
And the paper models this absolute awareness mathematically as an identity element, postulate A1.
Correct. In group theory in mathematics, an identity element is a value that doesn't change other elements when combined with them.
Right.
For example, in multiplication, the identity element is 1. 5 times 1 is 5. In addition, it's 0. 5 plus 0 is 5.
It interacts, but it doesn't alter the information.
Exactly. Dupke models absolute awareness as carrying zero information. It just illuminates whatever information is placed in front of it.
And this solves a massive problem we talked about earlier.
The erasure.
Yes.
Yes.
Because absolute consciousness carries zero information. That is precisely why it survives the complete baseline reset at the Big Bang. Postulate C.
You nailed it.
When the initialization machine hits format, it wipes the ledger completely. Your memories, the 2035 laboratory, the physical universe, all the information is erased to balance the thermodynamic debt.
Right.
But the mirror of awareness remains utterly untouched because it was never written on the ledger to begin with. It is the always-on substrate.
Precisely. The contents are erased, but the container remains. And this theoretical physics model leads Dupke to a very specific, deeply personal, operational corollary, which he calls the resolvability budget.
Oh, this was the part of the paper where the cosmic scale suddenly collapsed down into my own living room.
It gets very real, very fast.
The paper applies quantum phase tracking mathematics directly to human attention.
He borrows from a theoretical framework called HCOPL, which looks at how observers resolve quantum branches. And the math suggests something quite startling.
Which is?
The sampling depth, the computational power required by the substrate to hold a coherent branch of reality-stable scales with the square of the observer's internal noise.
The square of internal noise. Let me make sure I understand the practical application of that math.
Sure.
If my internal mental noise, my ambient anxiety, my doom scrolling on social media, my fragmented attention from constant context switching between emails and text messages, if I can manage to just have that internal noise.
Yes.
I don't just have the computational cost on the universe, I quarter it.
That is exactly what the math implies. Your attention is not just a personal psychological trait, it is a fundamental system resource of the universe.
So when you look at modern society, an attention economy that is literally optimized by algorithms to promote constant outrage, hyper-distraction, and endless doom scrolling.
We are deliberately degrading the system resource needed to initialize the universe.
Wow.
We are running the most demanding, universe-generating computation in the history of existence on a hardware substrate that we are actively keeping noisy for the sake of advertising revenue.
That is a deeply unsettling perspective. It frames mindfulness not as a self-help tool, but as a literal cosmic necessity.
Which is why the paper proposes a maintenance protocol for the reader. Dupke calls it the pre-flight protocol.
Okay, what is it?
But it is very careful to note that this isn't about being hypervigilant or getting angry at yourself when your mind wanders.
Because of the asymmetry of awareness, right?
Exactly.
The paper points out that when you lose awareness, when you get swept up in a daydream or a spiral of anxiety, you don't actually know you've lost it in the moment.
No, you can't. You can't catch yourself drifting away because the part of you that does the catching is the very thing that drifted.
Yeah.
The asymmetry guarantees that the lapse always goes unnoticed until after the fact.
So you can't prevent the wandering. What is the mechanism of the protocol then?
It's simply about the mechanism of returning, structuring your experience to constantly prompt a return to the baseline of absolute awareness. To achieve this, the paper embeds a simple pointer question, an instruction for the reader to ask themselves continuously.
And the question is just, are you aware of yourself right now?
Yes.
So let me pause right here and actually do this.
Yeah.
I want to ask you, the person listening to this deep dive right now,
Yeah.
are you aware of yourself?
Just check in.
For the last 50 minutes, were you completely absorbed in the concepts of time loops, general relativity, quantum error correction, and diffusion models? Had you completely forgotten the feeling of the chair you were sitting in, or the sensation of your own breathing?
It is a profound, almost physical shift when you actually check, isn't it? The conceptual machinery stops, just for a second.
It does. And, well, this brings us to the final part of our discussion, the twist.
Yes.
I have to completely shift my tone here, because we need to talk about the very end of this mathematically dense, incredibly rigorous 17,000-word paper.
The author's note on the final page.
Yes. You read through the entire Ouroboros Singularity hypothesis. You wade through the Gödel metrics, the ledger balance postulate, the complete baseline reset, the convergence indices of quantum AI.
All of it.
You get to the very end, and the author, André Dupke, includes a final note.
He confesses.
He confesses that the core of the hypothesis, the Ouroboros loop, the machine generating the Big Bang, the ledger balance, is entirely fabricated.
It is a work of speculative fiction, disguised as a peer-reviewed physics paper.
I have to admit, when I read that note, I felt this sudden shock, followed immediately by a profound wry amusement.
It gets you.
We were perfectly outwitted. I bought in completely.
But this raises a vital question, and it's the reason we still dedicated an entire deep dive to this paper.
Right.
Why write a fake physics cosmology using entirely real technological facts? Why go through the agonizing mathematical trouble of building a watertight, logically consistent framework?
Because, to reiterate, the tech facts are real. Google crossing the QEC threshold in 2025, NVIDIA's sub-4 microsecond NVQ link, AI self-coding diffusion models, synthesizing quantum circuits.
It's all real.
All of that is 100% factual and educational. We truly are on that technological trajectory.
Yeah.
But the overarching connections he made between them.
The connections were custom cut. Dupke built a trap for the human intellect. He built a meticulously logical, utterly fascinating cosmological model to prove a singular philosophical point. He wanted to demonstrate to the reader experientially exactly how easily the human mind can be hijacked by its own fascination.
Right.
He wanted to show you how easily you can be mesmerized by complex ideas, by the grandeur of time loops, the elegance of quantum thermodynamics, the existential stakes of a 2035 singularity, to the point where you completely, utterly forget the simple, undeniable truth of your own existence in the present moment.
The entire 17,000-word paper was a giant, elaborate mindfulness bell.
Exactly.
He literally dropped that question, are you aware of yourself right now? 3 separate times in the text.
He did. And each time it acts as a circuit breaker. It pulls you out of the complex conceptual maze he built for you and drops you back onto the blank canvas of absolute awareness.
It's like someone building a massive, incredibly intricate escape room.
Oh, that's a good analogy.
It's got laser grids, cipher codes, hidden magnetic compartments, and UV lights. And you spend an hour sweating, furiously trying to solve the puzzles and unlock the door, only to realize the door was never locked in the first place.
Right.
The whole point of the room was just to see how long you would stare at the wallpaper before you remembered to just turn the handle and step outside.
That is a perfect analogy. The complexity of the argument was a feature, not a bug.
It was bait.
Yes. It was designed to pull you away to perfectly prove the paper's point about the asymmetry of awareness. When you are lost in thought, you do not know you are lost.
Yeah.
You can be reading 17,000 words about the majestic origin of the universe, and in the process, completely lose touch with the basic fact that you exist. The only cure to the trap of fascination is to drop the concepts and simply exist.
So as we wrap up this deep dive, what does this all mean for us? The technological milestones we spent so much time unpacking today, from real-time quantum decoders intercepting decoherence to AI models utilizing inverse generative synthesis, they are entirely real.
Absolutely.
They represent an incredibly accurate snapshot of where our engineering stands today. We are building systems of unimaginable complexity.
We are. The engineering trajectory is factual, and the challenges of latency and scaling are exactly what the industry is currently tackling.
Right.
But the grand cosmic loop, the Ouroboros Singularity itself, was a beautifully crafted story. It was a mirror, angled perfectly to reflect our own distracted minds back at us.
It really makes you evaluate your daily life. The Ouroboros loop was fiction, but how many other closed loops do you run in your own head every single day?
So many.
How many complex anxieties about the future, obsessive career forecasts, or elaborate imaginary arguments with people in the shower are just incredibly detailed science fiction stories your brain is telling you.
Yeah.
Stories that do nothing but pull you away from the plain, simple fact that you are sitting here breathing and alive.
It's a lot to think about, or rather, not think about.
Yeah.
So one last time before you go and before the next thing grabs your attention, are you aware of yourself right now?